Hello everyone, glad you're able to join us today. Welcome to our tutorial on design approaches to battery racks, packs, and modules. First off, I'd just like to thank PlugVolt. Thank you for organizing and hosting this webinar series. You guys have been great throughout this all. So as mentioned, I'll just give another brief introduction of who I am. So my name is Alex Ramji. I'm a senior hardware designer at Nuvation. I manage our energy solutions and subsystems group. I work out of our Waterloo Design Center, which is located in Ontario, Canada. And my team is responsible for two main areas. The first being product offerings, which take our BMS as the starting point and further integrate them into higher level solutions. Our main focus here being on creating products that are simplified to smooth out the integration efforts for our customers. And the second area is development of complete energy solutions, such as battery stack designs and containerized systems. So this is a three-part webinar series on leveraging the BMS to build a better energy storage system. Through these webinars, we'll be exploring how energy storage system developers are utilizing the battery management system to gain greater control of their assets. This is the first tutorial of three. The next tutorial will be on battery stack design for UL 1973 certification. That one will be on August 13th. And then the last tutorial of the series will be on gaining more visibility into your energy storage system. And that one will be on September 9th. So there's some great content to look forward to in the coming weeks. For today, here's our agenda and what we'll be going through. We'll start off with an introduction to Nuvation Energy. Next, we'll look into why we care about energy storage and what applications it can be used for. Then we'll look at battery system architecture and what makes up a battery stack. We'll then look at design strategies for battery stacks. We'll briefly touch on system level design, mainly look at battery energy storage systems. And then we'll give an overview of some of our products and how they could be used to simplify your stack design. And then last, we'll be holding a Q&A session at the end. So we'll get right into a company overview. So Nuvation started off in engineering design services back in 1997. Since then, Nuvation has completed over 1,000 customer projects. To expand beyond just services, in 2008, Nuvation Energy was formed with the focus on developing battery management systems. From day one, our vision has been to create a highly configurable product to allow compatibility with virtually any battery system. We developed our 1250 volt high voltage battery management system, to which we are now on generation 4, as well as our low voltage BMS to address the various applications that are 60 volts or under. We then more recently expanded our product offerings to include more complete system level products to help simplify bringing energy storage systems to the market. This includes our stack switchgear, battery control panel, and end controller EMS, as we'll talk about later on. We also have kept our roots in engineering design services and still offer design service and integration support. We've designed full battery stacks and even full containerized battery energy storage systems. Nuvation has 2 office locations. Our headquarters is in Sunnyvale, California, and our design center is in Waterloo, Ontario, Canada, which is the office that I'm located out of. So here we've got a map of our various installation sites across the world. We are now well past 100 installations, which is very exciting. You can see the greatest number of installations are within the United States and Canada, as that's where we're physically located. However, we do have systems all over the world and continue to expand our reach. Some of the more cooler system locations include a microgrid system for private islands off the coast of Panama, as well as an energy storage system for the island of Laifuka in the Kingdom of Tonga. We actually had the king of the island visit and bless the energy system after commissioning was complete. There's not many energy systems out there that can brag about a king's blessing. We also recently had our first systems deployed to Africa a few weeks ago, which means that Nuvation Energy has systems in every continent in the world except from Antarctica. Very similar to who's tuning in to this meeting. Okay, so why energy storage? Well, for one, and a very important one, there's a market for it. We've seen in the last decade, it's been a growing market and is expected to keep growing at phenomenal rates in the coming decades. This plot here shows the global gigawatt of energy storage installed. Where we're at today is barely noticeable on the chart. But as you can see, over the next 20 years, there's huge growth, and by 2040, we're expected to be over 50 times of where we're at today. So there's certainly a market here, and it's a good time to be in energy storage. So now let's take a look at what these energy storage systems are being used for. I've got a list here of some of the more common applications, starting with in front of the meter. So with that, we've got energy arbitrage. This is where we store energy during low consumption periods and use the energy during high consumption. We've got flexible peaking resource. In this case, the system provides peaks of power when required by the grid. Then there's frequency regulation. That's regulating the supply and demand on a second-by-second basis to keep the grid frequency within required bounds. There's reserve capacity, where fast-acting battery systems can supplement generators and allow for them to operate without a reserve capacity. There's voltage support. Here we are stabilizing voltage through reactance management using the battery storage as a load. There's black start, where we re-energize other systems without power from the grid available. And finally, there's transmission and distribution deferral, which is as demand for electricity increases, adding battery storage can defer or even remove the need for additional upgrades in equipment. Then if we look at behind the meter application, there's also a number there. We've got demand charge management, where reducing the maximum power draw from a grid can create significant cost savings in the commercial and industrial sector. There's time of use management. Here we store energy when the demand and prices are low and use it during peak times when the prices are higher. There's self-consumption from solar. With this, we can reduce or eliminate reliance on the grid by pairing solar plus battery storage. And then there's backup power and uninterruptible power systems, where during a power outage, stored energy can be used to continue operations without interruptions. So wow, there's definitely a lot of applications that we see energy storage systems being used for. The last reason we'll talk about why energy storage is the renewables integration. This is also very important. We have to focus on cleaner energy resources because our planet needs it. Solar and wind are two of the most common renewable energy resources, but we know that with these applications or with these resources, both of them can be intermittent at times. Therefore, in order for these resources to be effective, they need to be paired with energy storage. One interesting claim that we heard is the president of PG&E, one of California's largest utilities, stated that they have built their last ever coal, gas, and even nuclear plant. But what's even more interesting here was this wasn't solely an effort to be more green, but actually because solar and storage is now their cheapest way to make energy. Something that was definitely not the case a number of years ago, but is so now as the cost of energy storage is coming down. I mentioned earlier one of our installation sites were private islands off the coast of Panama. I want to come back to that example with this topic. We've got a picture here in the top right of a group of energy storage containers with a grid of solar panels all around it. This project was an energy storage system to completely microgrid these sets of islands using solar plus battery storage. It was a great example of where what used to be an extremely expensive system actually became the most economic way to keep this group of islands powered. Okay, so we've talked about why we care about energy storage. So now let's take a look at the battery stack architecture. We'll start by analyzing what's going on in this diagram. Here we've got an example of a battery system. In this case, it's a two-stack battery system shown for visualization purposes, but the number of stacks in parallel can be much more for a larger system. Since there's a lot going on here, we can break this down piece by piece. So here we're focused on a single battery stack. What we can see is that the stack is composed of a string of batteries, cell level BMS, a method of thermal management, there's stack level BMS, and then not shown specifically in the diagram, but also required is racking and then interconnects and cabling. Breaking it down even more, we can take a look at the batteries and the cell level BMS and see how they integrate. This is how we are getting data from the battery cells, and in our case, it's a product called our cell interface. If we take a closer look, we've got two cable harnesses that are coming from the BMS to connect to the batteries. The first is the voltage tap harness, which allows us to get cell voltages, and the second is the temperature harness to allow us to get temperature readings of either the cell or the module. The cell connections will be on every series connected cell in the battery stack. The cells are connected directly cells connected directly in parallel will have identical voltages and thus only require one measurement. This is also where balancing occurs to ensure cells are closely matched and when charging and to prevent state of charge drift over time. This is particularly important when dealing with lithium-ion chemistries, which aren't as forgiving to under and over voltages. Okay, so zooming back out, we then see that the cell interfaces communicate this information back to the stack level BMS. This is achieved through a daisy chain of communication between the cell interfaces as shown in the diagram. Next, we've got the stack level BMS. In our case, we call this the stack switchgear, and it's the interfacing device between the battery and the rest of the system, which is typically a common DC bus or a power conversion system. The stack switchgear is composed of additional BMS hardware, along with components such as contactors, fuses, stack voltage and current measurement, pre-charge circuits, e-stop monitoring, and other supporting hardware. The stack switchgear receives all the battery data from the cell interfaces and is responsible for monitoring the state and safety of the battery stack. It's the device responsible for connecting and disconnecting the stack. It also provides current limits for either an external controller or a power conversion system. As well, it's the device that detects a fault and disconnects the stack if the system is being operated in an unsafe condition. On the side, we've got a snippet from our operator interface where you can see an example of some of the stack details displayed, which would come from our stack switchgear. So you can see things like stack voltage, stack current, the state of charge and depth of discharge, as well as in the bottom right, you can see some parameters for current limits as well as cell balancing. So now we've seen how the stack level BMS and cell level BMS play a part in a battery stack. In addition to that, the stack is also composed of racking to house everything, the interconnects and cabling, both for the power connections and the BMS, and then typically some form of thermal management system. In this example, we've got a chain of fans, which are also controlled by the stack switchgear and enabled based on the cell temperature readings. So now that we've looked at a single battery stack and broken that down, if we take one step further back, we've then got a multi-stack system. Here, each battery stack is connected to a common DC bus, which is also often connected to a centralized power conversion system. For a multi-stack system, we need some sort of device that can manage the multiple stacks in parallel. For that, we have a product offering called our battery control panel. What this product does is aggregate data and control of multiple stacks by connecting to each stack switchgear in the system. It then presents the multi-stack system as a unified single battery that can provide battery details for the entire system to the power conversion system or an external controller. Lastly, at the system level, there's typically an e-stop circuit which can be tied to the stack switchgear for fast-acting disconnection of the system in the event of an emergency. So that's the entire system breakdown. You can see there's multiple layers of BMS product in order to provide the necessary management and ensure safety of the battery stacks. So now we'll start looking at designing a battery stack. But first, it's important, like with all design tasks, to start with the requirements. As we'll soon get into, there are many factors that come into play when designing a battery stack. There doesn't exist a single solution to meet all needs, but rather there are many trade-offs along the way. As we look at designing an effective battery stack, it's important to understand the application. There are many design factors to a battery system. Therefore, in order to design a cost-effective solution, understanding how the stack is going to be used is crucial. The application leads to the system requirements, such as system ratings, the required storage capacity, and the expected system life or operating life, as we'll touch on briefly. Earlier, we mentioned a wide range of applications where we see energy storage used in the market. We won't break those applications down further, but in general, applications tend to fall into one of two categories, either a power or an energy application. What I mean here is, for an energy system, for example, we see systems are typically required to operate at or around half C or lower. Half C meaning a maximum output power equal to half the energy or the energy storage capacity. For example, if we take a 500 kilowatt system that stores 1 megawatt of energy, that's considered a half C system. When we talk about a power application, the durations are often much shorter, but the discharge rates are higher. 1, 2, or even up to 5 C is sometimes required by applications. Understanding the power requirements often will dictate the PCS selection and in turn typically impacts the voltage range of the battery stack. It also impacts sizing and capability of the other equipment in the system. As well, there are many thermal implications to consider based on the power ratings. Understanding the energy requirements determine the capacity of the system, which in turn impacts the battery size and/or the quantity of stacks required in parallel. And it's really important to remember that batteries degrade over time. So often the end-of-life performance is what needs to be considered when sizing the system. Next, we have to consider the daily cycle count, or for applications where cycles are not necessarily straightforward, it's the equivalent cycle counts that we care about. This impacts the thermal management requirements depending on the duration and frequency of rest periods. Said another way, the duty cycle of the system. Last, the expected life of the system is an important requirement as it has impacts on the battery selection. It also impacts what servicing and maintenance is required throughout the life of the system. The daily cycle count is also a factor when the system with the system life, since cycling the system more frequently does age the system more quickly. So now that we've got an idea of some of the types of requirements, we can start looking more closely at the stack design. As mentioned earlier, there is no one solution that rules them all. Designing a battery stack is very application specific. On the right side, we've broken down the different sections of a battery stack that we'll be walking through. We'll look at things like trends in the market, things to watch out for, and trade-offs when applicable. Leading it off, we've got battery modules. So batteries come in a variety of different forms, each of which excel in different attributes. Some of the key attributes that we'll care about are things like discharge rate, energy density, and cycle count, but there's also many more beyond just these. I'm sure we're also all aware that there's different battery chemistries. The most common we see today are LFP, NMC, and lead acid, but again, there are many others. With LFP, generally, they are considered safer when it comes to fire propagation. For NMC, they're generally able to support a higher energy density. And with lead acid, they are generally able to withstand more extreme conditions and can also be a more cost-effective solution for applications that are not space conscious. Battery cells also come in a number of different form factors, such as cylindrical, prismatic, and pouch. With cylindrical, the advantages are ease of manufacturing and good mechanical stability. With prismatic cells, typically they have large single cell capacities and can be easier to work with for mechanical integration. And then with pouch cells, generally they have a higher packing density. We won't go further into details here specifically about cells, but I just wanted to give a highlight that there are many different options available in the market. When selecting a battery, the cell capacity and configuration is also very important. At the module level, we've seen a trend in the capacity increasing. This can be achieved by two methods. One method is using larger capacity cells within the module. This is very commonly seen with pouch and prismatic cells. The second is combining more cells in parallel at the cell level. The challenge here is ensuring that the cells are better matched so that they experience less drift over time. If one cell is aging quicker than others, it creates a limitation on all the cells connected in parallel with it. Increasing the capacity at the module level is really beneficial when it comes to BMS costs. By increasing the capacity, it can reduce the amount of duplicated hardware. Ultimately, you are managing more energy with the same quantity of battery management system, which leads to a reduction in dollars per kilowatt hour. For example, if we consider a 10-stack system and double the capacity of each individual battery stack, well, then you can achieve the same amount of energy by using a 5-stack system. By us telling you this, you're actually buying less BMS. Being a company that provides a BMS, that doesn't sound like a very good sales strategy. But ultimately, it's the correct design approach, and we acknowledge that for us to be successful, our customers need to be successful too. Battery management system integration is also an important factor for module selection. Previously, we mentioned that at the cell level, the BMS is responsible for cell and temperature connections, as well as monitoring and cell balancing. The integration dictates how reliable the input data is and is important to ensure that these are secure and robust connections. To mitigate this, our BMS is equipped with a SenseWire conductivity algorithm, which is continuously checking the integrity of the cell connections. If the integrity of the connections is poor or weakens over time, the system can notify the user of the issue. We have a great example of how this feature identified an issue in one of our applications even before commissioning had occurred. In the plot shown from the system, you can see a relative measure of conductivity for the cells in the system. The higher the value, the higher the conductivity. As you can see, as this data is grouped, we can see clusters identified, mainly into three clusters. In particular, there's a notable cluster with cells of lower conductivity compared to the majority of all others. This is the cluster highlighted in yellow. Upon further investigation, the root of this issue was actually found to be a battery manufacturing defect within the battery modules. Had this not been identified early on, the system would have gone into field operation, and eventually the issue would have arisen, requiring expensive post commissioning downtime. So we can see that in order to ensure we have good data, we need to make sure that the integration with the battery modules is very good. Moving on, the last factor we'll talk about regarding battery modules and trays is the handling and installation. This is key for minimizing the cost of in-field or on-site work. One question here is if lifting equipment is required. 50 pounds per person is generally considered to be the safe limit for workplace safety. And then beyond 2 people and handling a battery starts to become a pretty awkward scenario. So in many cases, that means once you're past 100 pounds, which is not too uncommon for a battery module, it's quite likely that lifting equipment will be required. In that case, provisions with the module and/or the rack need to be thought through which is much easier to do earlier on in the design. Next, we're on to racking. When it comes to racking, here's some factors to consider. First, there's manufacturing and installation. For low volumes, it often makes sense to use off-the-shelf or open frame racks. This can also be true for prototyping. However, as you get to designs for higher volume, you need to plan for ease of manufacturing, assembly, and install. For battery stacks that are part of a UL 9540 system, then fire propagation testing, which is UL 9540A, is something to take note of. Depending on the battery module selection, if not contained within the module, fire propagation may need to be mitigated at the rack level. In this case, fire barriers or metal sidewalls may be required. Next, energy density may be another important factor for your system. This is often the case for containerized solution, where space is a premium, but can also be the case for an indoor system. Packing racks more densely requires better integration with the modules, so it's a lot easier if you're designing the two in parallel. But keep in mind, creating an energy dense design does often lead to more challenging thermal management. For rack design, grounding is also important, both to ground the racks to earth, but as well to ground trays to the rack. Planning convenient ways to accomplish this greatly simplifies installation, and bonding ground wire should be used because grounding through hardware is typically not permitted and is not a good practice in general. Last, depending on the end site location, there may be seismic considerations for your rack design. If a site is located near an earthquake-prone area, additional structural rigidity will assuredly be required. Moving on, the next area is interconnects and cabling. When it comes to cabling, there are power cables as well as the BMS cables. For power cabling, you must ensure the cable is sized appropriately based on the local electrical code. This is sometimes based on the ratings of inline fuses within the system. Other times, this may be based on joint temperatures of the components that they connect to. And then, of course, you need to make sure that the cables are insulated sufficiently for the maximum voltage of the stack. And don't forget about the installation process. When dealing with high voltage connections, PPE such as arc flash suits and insulated gloves are typically required. If you've ever worn one of these suits before, if you've never worn one of these suits before, you may not be aware of how much dexterity is lost when wearing one. It's so important to ensure that the procedure for installing power cables is doable even when limited by the PPE that's required to be worn. Then with BMS wiring, there are three categories: the voltage, temperature, and communication cables, as we've mentioned. There could be a lot of BMS wiring, so detailed planning around the routing and lengths can lead to a huge installation effort savings. Next, we take a look at thermal management. There are three thermal management systems we commonly see used, those being forced air, HVAC, and liquid. Often forced air and HVAC are paired together. With these systems, there is often less upfront cost and it's a simpler architecture. The HVAC and ducting industry is very well established and understood, so it results in a much easier implementation when using this cooling mechanism. However, we are starting to see liquid cooling systems entertained more frequently. Some of the benefits seen with liquid cooling systems are the ability to increase the energy density of the system, an increase in power capability, and an increase in battery life. This is because with a liquid cooling system, you can get the cooling medium much closer to the source and exchange the heat quicker. So while there may be more upfront cost to a liquid cooling solution, it can lead to long-term savings in some applications. Now we are into the safety and control components of the battery stack. Here we've got a list of some important stack level features. That includes connecting and disconnecting the stack, stack voltage and current measurements, short circuit protection, fault handling, pre-charge circuit, fan control, as well as e-stop monitoring. If we take a look at this diagram, we can get a little bit of insight as to how we're implementing this functionality. We can see here contactors are used for connecting and disconnecting the stack. Under a fault condition, contactors are also opened. Inline fusing provides the short circuit protection. These fuses need to have extremely high breaking capacities in order to break what can be very high short circuit currents for a battery stack. It's very common for us to see short circuit currents in the 10,000 amps or tens of thousands of amps. Precharge is implemented using a current limiter and an additional contactor. The precharge is used to limit current when connecting multiple stacks together, also when connecting to a PCS, which generally has a very large capacitive bus. Without the limiting of current, you can see overcurrent in these connections, as there could be voltage differences between adjacent stacks. And then stack voltage and current measurements are taken internally using the smarts behind this all, the battery management system. So this is our last section on stack design. As you can see, there are some BMS modules within the stack switchgear, along with the cell level BMS as discussed before for interfacing directly with the batteries. Expanding on the BMS, the purpose of it is to provide the ability to report. That includes things like real-time voltage and current, state of charge, and depth of discharge. It provides the ability to capture cell voltage and temperature measurements, as well as conduct cell balancing. It also generates current limits, which are required by either a site controller or the power conversion system. And finally, the BMS is able to detect faults within the system. This includes faults such as over and under voltage, current, or temperature, and can be either at the stack or at the cell level. It also has the ability to detect faults that may be due to communication, installation, or hardware, which can be very helpful when commissioning a system to have more insight where things may not be correct. So there you have it. You combine everything we've discussed so far, and you've got yourself a battery stack. But before we call it a day, there's one more thing we want to consider, and that's certifications. For battery systems, we are seeing a huge increase in requirements around certifications. UL 9540 as well as UL 9540A are the most common standards that we're seeing today that are applied to energy storage systems. As part of a UL 9540 system, there's a power conversion system that needs to be listed to UL 1741, as well as battery stacks that are listed to UL 1973, which we'll take a closer look at. Within a UL 1973 certification, there's a construction review and a performance testing for the battery stack. There are also two additional standards of interest which are applicable for the BMS. Those being UL 991, which pertains to the hardware on the BMS, and UL 1998, which covers the software for it. With UL 991, the analysis is based on product design schematics, and in particular, conducting a failure mode and effects analysis. As well, it analyzes environmental testing to ensure robustness of the product in the field. Then for UL 1998, it analyzes the software with a code review, and it also requires testing and certification of a specific binary image for the system under evaluation. We've got some exciting news to share regarding these standards. Our BMS recently received UL recognition for UL 1973 by completing both UL 991 and 1998. Our BMS is the world's first configurable BMS to be recognized under UL 1973. What that means, what we mean by configurable is that it can be configured to work with different chemistries, different battery manufacturers, different stack voltages, and battery topologies. When we approached UL, they actually didn't have a process for completing functional safety on a configurable BMS. but through working with them, we were able to invent a new process. And now we can offer, now that we've got through the UL 1973 certification, we can offer a BMS that can cut certification time and costs for our customers. We'll now briefly discuss the system level solutions, or what are more commonly referred to as battery storage systems. Battery stacks are often a building block to a larger system, as we saw with the multi-stack example early on. It's quite often that this is the case, as many applications have power and energy requirements far beyond what is feasible from a single battery stack. In the images shown, we designed a containerized solution capable of providing up to 2 megawatts of power for our 15-minute profile. The energy stored was just under 600 kilowatt hours, and the system was composed of 20 battery stacks, with batteries capable of discharging up to 4C. In this case, this was very much a power application, and one of the toughest challenges encountered was dealing with the thermal management of the system. You'll see in the image on the right, all the door-mounted fans required to pull air through the racks. Behind these racks, the HVAC ducting dropped cool air so that it could be pulled through the racks and across the batteries. The system was also equipped with 2 5-ton HVACs. This was an example of a containerized solution with internal access. For the last number of years, this was a common container design, as it was thought to provide easier access for servicing and maintenance of the system. There are benefits to it, as it does provide shelter from the elements when servicing, something that is a huge benefit when working in a heavy arc flash suit, particularly in hot and humid climates. However, the trend we are seeing now is towards solutions with external access and removable panels on the outside of the container that provide access to the battery racks. This is because it has the added benefit of increasing the energy density, as the 3-foot aisleway can now be used to store more energy. In the 2 diagrams here, the top having internal access and the bottom having external access, you can notice a significant amount of increased space for the battery racks in the lower diagram. Okay, so the last section to cover today before we open the floor for our Q&A is our products. We've seen our products pop up a number of times throughout this presentation, so I just want to summarize them as we close. First, we've got our cell interface. As explained, this product directly interfaces with the batteries for cell and temperature measurements. Multiple devices can be daisy chained together to support stacks up to 1250 volts. It can also be configured to be used with virtually any battery chemistry and comes in product variants of 12 channels and 16 channels. It also provides the capability to balance the cells and supports up to 8 thermistors. Moving up on another level, we've got our stack switchgear. This product manages the battery stack and combines our UL 1973 recognized BMS modules along with contactors, fuses, and a pre-charge circuit. It also measures the overall stack voltage and current. It can control cooling fans based on cell temperature. It monitors and reacts to the state of an e-stop system, and you can manually disconnect the stack from it. Our stack switchgear is currently offered to support systems up to 1250 volts and 350 amps. Last, we've got our battery control panel for aggregating data and control of multiple stacks. This includes a wall-mounted panel, our multi-stack controller, a power supply with UPS, all require networking hardware, a touchscreen display to access our operator interface, and a cellular modem. The battery control panel is able to support aggregation for up to 36 battery stacks. Then if you're not building your own energy solution, we also have relationships with multiple turnkey solution providers as shown here. If any of these interest you, you can reach out to Nuvation Sales for further details. So that concludes this first tutorial of our 3-part series. Be sure to register for the next 2 tutorials, which will be occurring over the next few weeks. The next tutorial will be battery stack design for UL 1973 certification. We touched a little bit on the certification, but to get more details, this webinar will be great. That one will be occurring on August 13th. And then the last tutorial of the series will be on gaining more visibility into your energy storage system. And that one will be held on September 9th. So I thank you for watching this webinar.